All right, yeah, I think we can get started. Let's see, this week, a little different. I don't think I'll be talking quite as long. Kind of wanted to just show you guys what I've done so far with the BigBird example notebook and kind of the I guess the current challenges that I've got with it, and then maybe some ideas that I have for directions we could go with it and what to explore. So yeah, so I was thinking we'd spend most of the time actually just kind of discussing that, basically deciding what to do next. So I think I talked about this maybe in a previous episode, but either way, we're working with what I've been playing with so far is this data set called the 20 news groups data set. We used it in our multi-class example. It's part of the BERT collection, or you can find it on its own on my site. It's pretty old, and it's essentially it's a forum with 20 different subtopics, and all of the samples are all forum posts. And yeah, they're here's kind of the table of the 20 categories. And if you look at them, there's a lot that kind of overlap. There's a lot of these miscellaneous categories that you could imagine, things that maybe belong in other categories ending up in there. So it's not the greatest data set because it's not actually human annotated. It's not labeled by a labeler. Instead, it's what people posted in these forum subtopics, which could be they could post something in the wrong place, right? So I think there's a fair amount of mislabeling in it, and then yeah, some of these computer topics have a lot of kind of weird terms in there. But the reason I'm working with it is that it does have some fairly long training samples, long pieces of text in it. And in the multi-class example, we did some experiments to figure out how much does the length of those training samples matter? Can you get away with just truncating the samples to make them fit easily in BERT? And what we found is that no, you cannot. Truncation actually is problematic for this data set. So there's benefit to being able to handle a longer input sequence. So because BigBird is all about handling longer input sequences, seemed like a natural choice. So yeah, about 10% of the 11,000 training examples are longer than 512 tokens. So to use BERT, there's a lot of truncation that happens. Yeah, and then I'll show you real quick there's not a lot of changes required to the code to use BigBird. So the BigBird tokenizer, I had to install sentence piece separately. So that's kind of new. And then yeah, there's a separate set of classes for BigBird. So BigBird tokenizer, BigBird for sequence classification. And then the main model that you can grab from Hugging Face right now is this guy, Google BigBird Roberta Base. So it was actually trained. They used Roberta as their initial checkpoint for training. So it shares the same vocabulary as Roberta. Let's see, and then when you load the model, some similar changes there. Yep, BigBird for sequence classification. And then there is this there's this additional parameter that you can set in from pre-trained, where you can choose whether to use the block sparse attention, which is kind of the main feature of BigBird that allows it to handle these longer sequences. Or if you have the GPU memory for it, you can turn off sparse attention and just use it using the original BERT attention mechanism. They call that original full. So yeah, otherwise the code's unchanged, I think. Yeah, with this data set, I use scikit-learn to grab it, and they actually have scikit-learn has like a document classification example where they use a multinomial naive Bayes classifier to classify these 20 news groups. What's great is it trains really quick compared to BERT, and it trains on the CPU. So it's definitely, you definitely want to improve over it, because it's I think it's much preferable. You know, if multinomial naive Bayes was good enough, it's got a lot of advantages because it's simple. So that gets an F1 score of 0.683. The highest score that I've got with BERT, truncating to 512 tokens, was 0.701. So we can improve over the baseline with BERT, so that's good. But I have yet to improve over the baseline with BigBird. So the highest scores that I've gotten so far, without doing a ton of hyperparameter tuning, I've run maybe 6 experiments or something. So not a lot yet. But yeah, the highest I've gotten with Sparse Attention, truncated to 1,024 tokens, and got 0.672. This took about 14 gigabytes of GPU memory, so can go a little higher on sequence length with a single GPU. But if I want to go further than that, I'll either have to cut the batch size down. I think this is a batch size of 4. Or switch to model parallelism and start dividing the model across multiple GPUs. And then with full attention, which I kind of expected this to perform, I was hoping this would perform just as well as BERT, because once you turn off the sparse attention, you're basically left with BERT. But yeah, they did do their own pre-training, so it's not identical. It's got a different set of learned parameters. But yeah, with full attention and 512 tokens, it's worse than the baseline, worse than vanilla BERT. Again, I haven't done a ton of hyperparameter tuning there, so it could be maybe there's a different learning rate or something that would push that higher. But so far, no luck. So let's see. Yeah, and then I did add, I added weights and biases logging to this example. So I think this is the first one where I've done that. We started looking at that with the Simple Transformers series that kind of abandoned towards the end there because we got kind of stuck and wanted to do something new. But let's see, yeah. So it is a nice way to basically capture the results of these experiments. It persists the results for me, and then is a nice way to create whatever plots that we want to compare. How does the accuracy look compared to batch size or learning rate, things like that. So I haven't been using. I just set that up recently, so probably half the experiments that I've run were not logged here. But yeah, just thought I'd point that out. So the example that we publish will include that. I think it'll be a nice feature. Let me look at my notes here a bit, make sure I've got, right, okay, so I've got some ideas for possible directions, and I think I've got some notes here about, yeah, some of those directions. Let's see. Other data sets, possibly, yeah. It's kind of yeah, let me just quickly read through these, and then I'll go back over the notes that I have on a couple of them, and then we can start talking about what to do next. All right, so batch size matters for model quality. It's not just a training speed thing. So if we have too small of a batch size, too large of a batch size, that can actually reduce our model quality. So I'm kind of limited in batch size. Did I write that up here? Yeah, so I'm limited in batch size because of the GPU memory. So what I could do is if I used multiple GPUs and did data parallel, I could effectively increase the batch size because I could have a batch size of 4 per GPU. If I have 4 GPUs, then I'm using a batch size of 16 because the gradients get averaged over all 16 of those samples. So that might improve quality. One thing to try. And then since BigBird is all about long sequences, we're not really getting into that long sequence domain yet. The longest I've tried so far is 1024. The author is actually saying in their paper, and Nick and I aren't entirely sure why this is the case, but they say that like sparse attention is only worthwhile above 1024 tokens. So they're I read that as like, don't really bother with this if you're not dealing with at least 1024 tokens in your inputs. So to go above 1024, I guess I could cut down on the batch size further, or I could look at model parallelism, which is something I haven't really explored yet. It seems like data parallelism is pretty easy to implement. Less clear to me so far whether model parallelism is trivial or kind of a big deal, but that's where you kind of, instead of having the model replicated, you actually like chop the model up and have different GPUs work on different parts of the model. And that can allow for larger model sizes or larger input sizes. And so something to look at there, the trainer class that Hugging Face has for kind of simplifying the whole training process kind of tickles my brain that maybe it supports model parallelism, so that would be something to check out. If it does, that would be great. Another possible direction would be to try a different data set besides 20 news groups. I did kind of confirm that like truncating below 512 tokens is bad for 20 news groups, but I don't know to what degree getting to 1024 tokens really helps. So there might be a better data set out there that's like has less of those labeling issues and maybe is even more benefited by the longer sequence length. So could be something to try. And then the last idea I had kind of last minute yesterday, I was like, maybe you could try like using reduced precision to consume less memory. Or I just got an email from Lambda Labs last week that they have these new instances with A6000s, which not familiar with those yet, but apparently they have 48 gigabytes of GPU memory per GPU. So if those are, if that's real, and just assume it is, and if I can actually get one, since availability seems to be a bit of a problem at Lambda Labs, that might be a pretty easy solution, at least for getting to those longer sequence lengths. So I do have, let's see, right, and then I had a few other directions that like we had kind of wanted to explore, but I'm not sure if they make sense yet. So I could run more hyperparameter tuning for 20 news groups, kind of using what I've already got, but it doesn't feel too promising because the memory kind of limits what I can do in terms of batch size. So and then we wanted to look at like we wanted to compare kind of a simple approach that we implemented in the document classification example is just this idea of chunking, where you take the long document, break it into chunks, run BERT independently on those chunks, and then I forget what we did in the example, whether we like ran classification on all 4 chunks and averaged the scores, or averaged the embeddings before running classification. But yeah, either way, it's kind of a simple strategy. So if you're going to do BigBird, it's like it needs to at least outperform that simple strategy, right? So that would be a cool experiment to run, but we need BigBird to like outperform simple truncation first, right? We need BigBird to like deliver better results, and then we can test whether chunking is worse or not. So can't try that yet. Yeah, and then another kind of research direction we had in mind was like it'd be kind of interesting to see, since the sparse attention reduces the computational burden of BERT, it'd be interesting to see how that kind of translates into savings for training time and memory usage. Maybe generate some plots there. But what makes that tricky to analyze is that we can't. BERT's limited to 512 tokens, so we can't we can't extend BERT out to 2,000 tokens and then compare its training speed and memory use to BigBird at 2,000 tokens. We can only do it up to 512, and again, the authors are saying like, well, sparse attention is only worthwhile above 1,024 tokens, so it sounds like it wouldn't necessarily be worth studying at or below 512. So that's another direction where I think we're kind of stuck. So I've got some ideas on other data sets, but I think I'll stop here and see if you guys have any thoughts, any questions. Yeah, let's see. I see one thing in the chat. Yeah, PyTorch Lightning. Okay. Yeah, so we've looked at PyTorch Lightning a bit. That's where the trainer paradigm came from. I wonder, my first thought there is like, let's see, so for GPU training, I'm gonna put that here under model parallelism. PyTorch Lightning. I think my first question would be like, can you load a model using Hugging Face transformers and then still apply PyTorch Lightning after that? Ah, okay. So they actually have a library for that. Okay, and it's kind of built around. Connected to the Hugging Face library in some way. So let's see. Let's get PyTorch Lightning. Zoom in here. Yeah. Lightning transformers. There we go. Nice. Latest release 8 days ago. Love it. I guess they've got, no, some of the commits are a lot older than that, so it's not brand new necessarily. Still zoomed in here? Feels small. There we go. quick commands, quick recipes. Yeah, so Harpreet, do you know, is it only kind of this command line utility with train.py, or is it something that you can like actually, you know, is it a library as well that you can write code against? Take a look at the code in here. Custom language model. Okay. Yeah. Well, that looks like something I'd probably have to go learn a little bit more about, but that does sound worth checking out, since I know, you know, yeah, I mentioned this idea here of like trying out the Hugging Face trainer, but we've heard that that's kind of like just stolen from PyTorch Lightning. So maybe just going straight to PyTorch Lightning would be a better route. Yeah. Yeah, so I think the goal, I'm trying to think back to like what's the goal for this example? We want to provide some starter code for using BigBird, and ideally, I want to provide some code where that demonstrates BigBird delivering on its promises, right? Because if it's just sort of like, if it's just code that shows you like, can't really get BigBird to work, then that's less interesting, but maybe still valuable in the sense of like, if you want to try it yourself, then at least here's some code for, here's our code. Here's what we tried. You can build from it. Hopefully, do better than than we've done so far here. Yeah, so I'm contemplating there, like, is it, how important is it, I guess, to get improved accuracy with BigBird versus like just kind of like showing a basic example of how to use it. I guess if using it effectively requires some of these techniques like data parallelism or model parallelism, then including those in the example would be really helpful, I think. So that would be one motivation. I'll try to capture that. I'm going to mute for a minute while I write that. Let's see. Cool. All right, so Nick, you're my fallback here. If nothing else, it's like you and I have got to decide what we want to do here. So, do you have any thoughts for me?
Yeah, I'm thinking that maybe basically the shrinking use case for BigBird is just anything that BERT can't handle, but that might contain information throughout the document that is longer than 512 tokens that needs to be attended to. So the use case might be more like if your document is longer than anything BERT can handle, then that's when you use BigBird. It's not necessarily, if it's around the same length that BERT can handle. It's really when BERT is not even an option.
Right.
So I think if you can find some, because I don't think it's even intended to be a competitor at a shorter document length. And it seems like with 20 news groups, you can get pretty satisfactory performance just by truncating these.
Right.
Whereas there might even be some long document data sets that are intentionally designed such that whatever the task is, information comes from the beginning and the end of the documents, so truncating would not be a strategy. And that's somewhat plausible that exists in like a real scenario where you need to know something at the very beginning of the passage that is answered at the very end. So if you can find something like that, that might work. But it sounds like for 20 news groups, I think historically truncating has always been a really good strategy.
Right.
In that, it doesn't completely hinder anything you're trying to do.
Yeah, they did. So in the paper, they've got two sets of, let's see, I'm going to zoom out maybe for a minute. I'll just scroll down here. And now I've got, here we go. So here's like the benchmarks they ran. So they basically did two sets of tasks, as I understand it. They did like question answering, which I feel like that's where I could kind of see what you're talking about, that like maybe the answer to the question is at the end of the article. It's like you gotta, and then they did do document classification. I wish they included, like, these are just the tables of parameters. I'd have to like look elsewhere in the paper to find the actual scores. But I don't know. Yeah, it's like I haven't. Well, no, I haven't looked. I was gonna say that like I don't know if you can like actually get your hands on these data sets, but or at least I know IMDb is public and probably this Yelp one, but these guys. But I haven't looked that hard, so I shouldn't say that.
I think Archive is out there, and Patents. I don't know what Hyperpartisan is, but Patents is out. I think I've seen Patents, but this might all be in Hugging Face datasets library.
Yeah. So I did try. I tried searching. The Hugging Face datasets library for the Patents dataset. I saw something called Big Patent, but I think it's probably different. And then it was interesting. I remember they said in the paper that, let's see if I can pull up those results, because it was kind of interesting what they had to say about that. Let's see.
Yeah. Ronan suggested, and I like this idea quite a lot, is compare the F score by the document length. So basically, to see if BigBird predicts well on the docs that BERT misses. So sort of figuring out, oh, is it the case that the ones BERT misses is due to them being too long, and BigBird picks up this slack when they're longer? I quite like that idea.
Yeah.
It would sort of validate this idea that under 512 tokens, it's not quite, it's not meant to be a competitor, but over 512, it's picking up the slack of these traditional transformer models in performing on something that's over 512 tokens.
Right. So it'd be, you would,
Thank you, Rona.
Yeah, thank you. So I think what you would do there is you would check, you'd look at like what samples, what test samples BigBird is getting correct that BERT got wrong.
Mm-hmm.
And see if you could, what would you do from there? Maybe like actually look at the samples and kind of apply some human intuition there of like, it's like, yeah, I can see how like those later tokens were key here. Is that right, or am I? Is there another way to approach that? Let's see.
I mean, possibly if you just run each of them on the same data set, you might see some distribution of correct predictions for BERT, maybe hovering in the shorter document length. And then for BigBird, it's hovering in the longer document length.
Right. Okay. Yeah. Without even looking at the actual training sample or the actual test sample text, you could just look at the length of those test samples
against correct predictions. So I mean, even just buckets of if it's 400 tokens and longer, what is BERT's score on documents that are 400 tokens and longer versus BigBird's, and then 200 to 300, 100 to 200, this kind of thing.
Yeah, okay, like, right, so kind of a histogram of different sequence lengths and then the number correct in each bucket.
Yeah. Or even probably more usefully is when it's documents, some of which are shorter than 512, some of which are longer. And basically you would be directly comparing the BERT strategy where we just truncate at 512 versus, BigBird where it can actually attend to the remaining tokens. And then there's sort of a direct comparison there of whether or not truncation is still a good strategy for whatever data set this happens to be.
Right.
Or whether, in this case, BigBird is actually adding value.
Yeah, so we could actually just take, we could filter the data set for just the long ones and see how BERT does versus BigBird there.
Mm.
All right, let me try to capture some of those steps. The buckets of sequence lengths. Filter down the data set. Samples. Yeah, maybe there we could even, chop the data set and take some of the training samples to use if we wanted. Yeah, it would be cool to see if like it'd be interesting to actually inspect the text of some of these samples. See if we can rationalize why the later tokens are important.
Yeah, in some of the QA data sets, I know in the papers they sort of, it might be hot pot QA, but a few of these they're intentionally saying, they're picking out intentional examples where you would need to basically combine two disparate pieces of text to get the answer. So it would be like, the brother of X is named blah, blah, blah. And then in another section, it would be, blah, blah, blah's father is so-and-so. And so the question that you might be asking of that is, who is the uncle of X? So you would have to, take this family relationship in this part of the text and this part, and then combine them to understand that the relation sort of travels through these two separate pieces.
Right.
So I think they discuss that. I'm not sure if it's, incredibly prevalent in the data set that they designed, but it does exist. And they are sort of pointing out that we want this to be a feature of the data set to see how well things do. It's sort of a challenging task where you can't just, look at one little phrase and sort of just by statistical correlation sort of, wing it and guess the answer and be right most of the time. You would have to do some reasoning. So in some of these QA data sets, there might be good examples that it would be fun to try out on BigBird.
Yeah, I see. So maybe like cherry pick some specific examples to try BigBird on. I wonder, it'd be nice if they've got like a do they have a fine-tuned QA model for BigBird? I think they might. How do you guys define models? Let's see, BigBird. Yeah. I'm pretty sure this guy is a question answering model. It's fine-tuned on the trivia data set. Trivia QA. Yeah, with BigBird for question answering head. Check out this. Ooh. Someone made a notebook. Got a peek at this. Load data set. There's the data set. This doesn't look half bad. Well, that's cool. I gotta check this out. Let's see.
Yeah, let's find out some good examples.
All right. Anything else in here? Number of global tokens. Yeah, it's the same as. Cool. Nice. All right. So let's capture that question answering. Looks like there's a. Okay. So yes. There it is. There's a nice looking notebook attached to this. All right. Yeah, okay. I think I'm liking this idea of looking instead of like trying to perform really well on a benchmark, to try to do a little more like small scale analysis here, where we're looking at just the longer sequences, or we're taking a QA model that's already been fine-tuned for us, and we can apply it to some examples that require that extra sequence length. Mm-hmm. And then some of these other topics, like the model parallelism route, like that might be kind of its own research direction. It feels like another little mini project. Same with some of these other trying reduce precision seems like its own mini project. I guess the A6000s, I feel like I got to at least try this. Because this would be really easy to try. A good standalone topic.
Yeah, but I think this works. Jay said, it may be worthwhile to validate the previous point you made that BigBird is not worth using unless token size is bigger than X, and somebody we've also seen reported X to be 1024. So I think that it's a good project, sort of. I'm also curious what the reasoning behind someone reporting that 1024 is, and I think we talked about this last week. Is that is that either someone did a complexity analysis and they said that time and space complexity wise, this only makes sense if your sequence length is longer than 1024, because the model is subquadratic, but sort of the coefficient in front of whatever the linear or log kind of time and space complexity is, it might be quite large, such that on smaller token sizes, a quadratic solution is still better than whatever the kind of time and space complexity of BigBird is. Whether that's like an algorithmic analysis kind of reasoning, or is it the reasoning that unless your sequence length is longer than 1024, this kind of sparse attention strategy is not going to be as good as sort of full regular transformer attention. So I'm curious about whether it's one of those or both of those, and to what extent it's really true. But yeah, that's a good point, Jay. Do you happen to know where you saw that figure? It might be in the paper, but I can't recall.
Yeah, let's see. There is they do say it in the
yeah, okay. Then sorry, Jay. Yeah, we've seen the same thing. I think it's in the paper, but I don't. Yeah. Let's see.
So the Hugging Face documentation does mention it. They say the following. You just throw that out there with no justification. And then I was trying to find, I feel like last week, Nick, you and I did the quick math on like, it's like if you add up with sparse attention and default settings, the minimum number of tokens is high. It's like 128 global plus 192 window plus 128 random. So, that's not that high. That's less than 512. It's 256 plus 182, whatever that is. Let's see, 448. So not 1024. Yeah, and then I do think I saw this in the paper as well. But anyway. But never, but no explanation. It's just kind of the same statement of like, no value, no benefit below 1024.
Okay.
One other thing under the kind of the memory arena is like I think Colab may give us access to more memory if you use their TPUs. Tried maybe a year ago to get TPUs working, but TPUs and PyTorch, in my limited experience, don't seem to mix well. Even though there's there's stuff out there on this. It's not like it's just flat out unsupported. But yeah, so it might require a jump to TensorFlow. Let's see. Okay. How are we doing on time? Oh, wow. A lot of time's gone by. Okay, well, yeah, I think I like the direction we've got here. So I think the summary here is that I'm going to try out those A6000s if I can get access, because that would just be neat to be able to actually run with the long sequence length. And that would be easy rather than going the model parallelism route. This seems definitely worthwhile, not hard to do. Just pick out some long examples, see if BigBird does better than truncation. And then I'll take a look at this. This may be, I'll have to read through this and assess it. But they're either this notebook is great and it can be just something we can reference as a great illustration, or maybe it's a concept that we can take and make our own example that is a little cleaner, which often seems to be needed, but maybe not here. Great. So yeah, TPUs work well if you use Lightning. Awesome. Thank you. Throw that in there. Not model parallelism. I have this funny issue with my keyboard right now where like I'll get like a stuck key and I'll get like 30 letter C's in a row or something. That's what that long series of spaces was. TPUs work well in Lightning. Nice. Do you happen to know how much memory is available in the the TPU that you can connect to in Colab is like, I don't know the right terminology. It's like one TPU, but it has 8 cores in it. So it's essentially like connecting to 8 GPUs. You kind of have to spread the load across all 8, I think, in order to use it effectively. But yeah, that was my question. My question was, how much memory do you get with the TPU? Because I've kind of wondered if it's like a lot better than the GPU. GPU is like 16 gigabytes. But I guess it is. It's spread out over 8 cores, so maybe it's misleading. Anyway, I think we've got time for like one sort of off-topic question, if anyone's got any, or if there's any other thoughts on BigBird. Definitely take them. All right, yeah, so Harpreet. So yeah, not BigBird, but if you have 1,000 manually labeled examples, okay, so a small labeled set and a huge unlabeled data set, like 100,000, and the goal is to iteratively create labels. Yeah. What do you think, Nick?
First, I think maybe the simplest to implement approach is to create, if you're under the assumption that the 1,000 manually labeled examples you have are, they are representative, pulled from the same distribution as your unlabeled data set, they're an accurate representation, you can create it's 1,000, so a very small classifier out of those 1,000, apply it to the 100,000, and basically take the most confident answers and sort of do some inspection and see if that's working. So if the very confident answers on either the yes or no, or I don't know if you're doing binary, but the most confident examples or predictions could then be used as sort of labels. If you look through a bunch of them and you say, okay, when it's very confident these are correct, then you can take those and add them to a training set and sort of create bigger and bigger models and sort of whittle down your data set until you run up against a wall, or you just come to some that it's not doing very well in the middle, in which case you might have to manually label sort of the middle ground questions or the middle ground examples. You can sort of iteratively attack it like that. There are, I don't know whether it's worth the effort, but I've done an example using semi-supervised or distant supervision. These are two sort of things you might want to take a look at, but these are sort of in the same vein. They are techniques, or they're sort of umbrella techniques about how to start sort of semi-labeling your examples. Probably the best research group that does this kind of thing is called Snorkel. I think it's from Stanford, or it split off from Stanford, but it's essentially you basically teach it some rules, and it sort of iteratively goes through your data set and applies sort of half labels. It's changed, I think, quite a bit in the few years since I've used it. It was sort of a medium amount of work to get going. create labels, but I think looking at whatever they have for the their latest edition is probably worth it. And I do see Snorkel on like glue benchmarks and super glue benchmarks pretty high up, so it does work quite well. But whether the effort to get it running is worth it, I'm not sure. I would start with this first example, just create a very small classifier, take the most confident predictions. If those are right, then you just treat those as ground truth, and you sort of iteratively go through. But I mean, there is a massive industry around exactly your problem, that people have a lot of data and a lot of it's unlabeled. So, at some point you might just run into the hard truth that you have to start labeling data. Yeah, Crowdflower or Mechanical Turk is actually, I think, pretty reliable. They use, they have some kind of like smart voting system that prevents bad decisions on your data. It depends how specific your data is or how domain specific. But these are all kind of ideas. Everyone has had to label their own data. It's not very fun, but it's a hard fact. So hopefully that helps you out a bit.
Yeah. I do like the small classifier notion. Like if you're just going for the most confident classifications, like BERT, it seems like outperforms older methods easily, but it's so heavy, right, to work with. And for like the 20 news groups example, that like multinomial naive Bayes, like it trains on the data set in like a minute using just the CPU. And does pretty well. So I feel like BERT is when you're like you're trying to eke out that extra performance. So for this, something simpler might make the work easier.
Something not transfer learning based, and then because it's easy to do this with BERT, I would worry that 1,000 examples isn't enough with a transformer based architecture, but it's worth trying. Okay, of course. Jay says, can maybe squeeze this out. Based on writing samples of several authors, is there a particular approach to identify which authors in unlabeled samples?
Seems like something you could throw BERT at. It's just as a classification problem.
That seems like the basic approach of you have multi-class classification. There are some models that are sort of like these are mostly generative models, but CTRL, I think, is the example off the top of my head. It's a couple years old, but it's a generative text model, but you can tweak sort of the style parameters. You tweak the style parameters, and it's sort of a creative, fun, generative text model. But you can say, I want it to be more, I don't know, American Gothic, or I want it to be more like Shakespeare. And so you can feed through the same prompt, and it will give you, depending on the sort of stylistic parameters, these different text styles. So there might be some insights in there to look at. There are models online that are like they're sort of like couched in the literary world, but you can write a couple paragraphs and it will tell you which famous authors this text sounds most like.
Nice.
So I mean, that's sort of a toy example, and it's sort of obvious if it's Shakespeare versus Jonathan Franzen or a very new author. But there might be some kind of ideas there. I don't know if they're finely tuned or anything, but it's worth looking at. So those are a couple places you might have some luck if you look around.
Yeah. I was thinking about like what's the COLA dataset task again? Is it grammatically correct? It's something like that, right? So
Yeah.
it's like BERT can, I think if BERT can look at, if it can classify grammar, then maybe it could classify style as well. I don't know.
Yeah. I think
Seems
there's
plausible.
some, I mean, it's another feature of language, so it should be able to handle style, but specific investigations into changing style, I'm not sure about. CTRL and those kind of things probably have a better handle on what style means and how one can sort of differentiate it with the model.
That's cool. All right. Well, yeah, let's wrap it up there. Thank you guys. Really appreciate the help. Excited to keep going on this now. So thanks for the insights. I'll see you guys next week.
All right. Bye, everyone.
Bye.